Okay. Hello students. In this session, I am going to discuss about structure and bonding of metal carbonyls. Metal carbonyls, that is example NiCO4, FeCO5. Okay, that one metal and carbonyl group or other ligand also, but there have some carbonyl group is there. That is compound is known as metal carbonyls. So metal carbonyl is a organometallic compound. There is metal is there, then carbonyl group, that carbon CO group, that is CO group, then metal is bonded to C, MC bond is there. Then this carbonyl group is an organic part, the carbonyl group. So it is very reactive. Some of the scientists saying it is the part of organometallic compound, then some other scientists saying it is not an organometallic compound. Anyway, in your syllabus it is an organometallic compound. Okay, then that CO group, that carbonyl group, it's a very good sigma donor and good pi acceptor. So that bonding of carbonyl group to metal can be explained according to MO diagram, molecular orbital diagram. You studied this one in your plus 2 classes. Okay, so I didn't go in depth because I think you know this one. Okay, then CO group, CO is atomic orbital, that is 6, 1s2, 2s2, 2p2. Then oxygen 1s2, 2s2, 2p2, 8 number. So this is a p orbital only. I didn't write s orbital. So p orbital, pi 2px, pi 2py, completely filled. Sigma 2pz, completely filled. Pi star is not filled. Sigma star not filled. Okay. So here this sigma bond, this sigma orbital is a HOMO, highest occupied molecular orbital. Then pi star, this antibonding orbital, is a LUMO, lowest unoccupied molecular orbital. This one you will study in your this semester, pericyclic reaction, organic chemistry. Okay, this is sigma bond is a sigma orbital, this is a HOMO. Then this pi star antibonding orbital is a LUMO bond. So here see, this sigma bond and pi star orbital is near to carbon atom, So most of the bond breaking and bond formation takes place near to carbon side. Very rare takes place in oxygen side, because this 2 is near to carbon side. Okay. Then this HOMO-LUMO distance is very low. That is this gap is very low. Then okay. Then CO is good sigma donor and good pi acceptor. I already said. So how CO is bonded to metal atom? So we can describe this one, this metal carbon bond. Here see, carbonyl groups a triple bond. Okay, then carbon is filled sigma orbital. Here carbon is filled sigma orbital, filled one sigma orbital. So it is donate electron. So carbonyl group, how many electron donate? 2 electron. You 18 electron rule, you studied this one. CO group, how many electron donate? 2 electron. So this 2 electron from this filled sigma orbital, it donate to metal empty d orbital. So the from carbonyl group, the electron from the filled sigma orbital, it donate to empty d orbital of metal atom. Okay. But metal character is positive character. Metal is a electropositive character. Carbon is carbanion character, negative charge. So metal is positive character. So it could not suffer this highly richness of this electron because its character is positive character. So metal tendency to donate to anybody. So this metal donate this excess electron to where to backbone to carbonyl group, backbone to carbonyl group. Here so that this metal empty d orbital is filled with this electron. So this filled d orbital backbone to carbonyl group pi star antibonding orbital. I think you got this concept. Pi star is a empty one. Pi star is empty one. So this filled d orbital of metal atom is backbone to empty pi star orbital of carbonyl group. That is called pi backbonding. Okay, you got this concept. First carbonyl group from the filled sigma orbital, it donate electron to empty d orbital of metal atom. So metal become highly electron rich. So that excess electron is backbone to carbonyl group of pi star orbital, empty pi star orbital. That is called pi backbonding. So then pi backbonding, the metal carbon bond is become strong, but carbon oxygen bond, the carbonyl bond is become weak. So metal carbon bond before it is a single bond, but it is act as a in pi backbonding it is become very strong. So it is act as a double bond like, but the carbonyl group is a triple bond. But when pi backbonding time it become weak, so it is become double bond. It is act as a double bond. It's not a true. It is act as a double bond because it is weak. It becomes strong. Okay, I think you got this concept. Okay, then this carbonyl group weakness and strength, this can be explained by knowing IR spectroscopy. IR spectroscopy, you know, IR spectroscopy CO group, the keto group, it is detect CO group mostly 1750. We will study this one detail in spectroscopy classes. Okay, so this when pi backbonding increases, stretching frequency decreases. What is the concept? That pi backbonding increases, the CO group become weak. So stretching frequency decreases. Pi backbonding increases, stretching frequency decreases. Okay, this also you know, stretching frequency is directly proportional to bond order. Bond order means CO bond order. Then stretching frequency directly proportional to bond strength. Stretching frequency inversely proportional to bond length. Okay, this also you learn. So I said you bond order increases, stretching frequency increases. So free CO bond order is 3. You know this one, 3 bond order 3. You calculated this one bond order. Okay, so bond order 3, the stretching frequency 2143 centimeter inverse. But when one metal is bonded to CO group, then some pi backbone started. So that bond order decreases 2.5. So that range is, that stretching frequency decreases here 2120 to 1850. Then 2 metal atom linked to CO group. So again the bond order decreases 2. It becomes 2. So again the stretching frequency decreases. Then again here 3 metal bonds bonded to CO group. So again the bond order decreases 1.5. So that stretching frequency also decreases. Okay, then factors affecting stretching frequency nu CO in IR. First one, electron density of metal. What happens? Electron density of metal, electron density increases in the metal. What happens? Pi backbonding increases. Pi backbonding increases means stretching frequency decreases. So here CO4 plus charge. Okay, NiCO4, COCO4 minus, FeCO4 2 minus. Here which one is low stretching frequency? Which one is low stretching frequency? Here see 2 minus. So electron density higher is here. Electron density higher, pi back bonding increases. So stretching frequency decreases. So here this is the lowest stretching frequency. When metal atom positive charge, it is high, pi back electron density low, pi back bond, then pi back bond decreases, pi back bond decreases, stretching frequency increases. So highly positive charge, stretching frequency higher, negative charge, stretching frequency lower. Okay. Next point, electronegativity of metal. That is means electronegativity increases, stretching frequency. If electronegativity is high, low pi back bonding, then what will happen? Low pi back bonding, stretching frequency increases. Stretching frequency increases. So here VCO6, electronegativity 1.4, here 1.6, 1.6, 1.8, 1.9. So here electronegativity higher is here. So normally low pi back bonding. So here is high stretching frequency CO group 2000. Okay. Then other ligands, if other ligands except CO, some other ligands is there. If other ligands is good pi acceptor, what will happen? If it is good pi acceptor, okay, here this metal here CO group, here one okay, here one ligand is there, one other ligand is there. So normally CO group donate to electron to here, so metal become rich. Then what will happen next? Metal is pi back bonding started, but here other ligand is there. So this is if it's a good pi acceptor, what will happen? These two started to competition to getting electron. So if it is good pi acceptor, the electron going to here also. It is divided to both. So donation of pi back bonding decreases to CO. Then what happen? Then what happen means the stretching frequency increases, pi back bonding decreases, stretching frequency increases. So here MOCO PF3 same compound, POME thrice, CO3 PY thrice. This ligand also different. This ligand different. So you know this order. You study this order, then only you can answer this question. Okay. Here NO is good pi acceptor ligand. NO higher than CO, then PF3, RNC, PCl3, PO. Lowest is pyridine. Pyridine is very low pi acceptor ligand, PY, pyridine. So you know this, you have to know this order. So here PF3 is the first one, PF3. So it is highest stretching frequency. POME3 means here toxic group POME3. Then next one here PYE, the last one. So this is the last option. Then second, first. So highest stretching frequency, this one. This one is a highest stretching frequency. Okay. This type of question will ask in net exam. You will give number of compounds. Then they will ask which one is the highest stretching frequency, or you write in a decreasing or increasing order like that. So you know this concept. That means highest electronegativity of metal, that is stretching frequency decreases. Negative charge, stretching frequency decreases. Then electronegativity of metal, electronegativity higher, stretching frequency increases. Then other ligand, if it's a high good pi accepted, it is stretching frequency. Stretching frequency, what happens? Stretching frequency decreases. Stretching frequency decreases. Then other one option also, if maybe sometime it coming, number of carbon ligand increases, stretching frequency decreases. So NiCO4, CO4 4 and FeCO5 5 number of carbonyl group. So carbonyl group number increases, the study frequency decreases. Okay. So you study this one. So if you have any doubt, you ask me through personally, through WhatsApp voice message. I will explain, because you have to learn this one. Then you solve number of questions. Then one book is there, Basic Organometallic Chemistry, alias Gupta. That is very good book. Then Huhi books, Huhi Inorganic Chemistry, Huhi textbook. Like that, some books is you taken and solve questions. Okay. Thank you.